morning and welcome to our new topic for this week, exponential functions. If you are watching this video and hadn't taken the poll that I posted in Google Forms on Google Classroom and also in the virtual learning syllabus for the week, then please stop this video right now and take the survey. And the question that I wanted to ask, or that I asked in the survey, is the following. Which would you rather have, $30,000 a day for the next 31 days, or a penny doubled every day for the next 31 days? And this is the really great introduction to exponents and logarithms and dealing with this new function and a lot about how it behaves and the modeling that it is used to create and stuff like that. So again, if you haven't taken that survey yet, then pause the video and go take that survey and then come back for the answers. All right, assuming you have taken it, let's move on from here. So the question really is $30,000 a day for 31 days or a penny doubled every day for 31 days. And the answer is not as obvious as it may seem, though some of you may be thinking, well, if he's asking this question, of course it's going to be the weird one because Mr. Winchell is weird and that's kind of the way he works. And if that is your reasoning, then that's fairly good sound logic and you would have been correct. If you chose the $30,000 a day for 31 days and added it all up, you would end up with $930,000 at the end of a month, assuming it was a 31-day month. If you chose a penny doubled every day for 31 days, you would end up with just a little bit more, almost $43 million. And that really has a lot to do with this thing called an exponential function, which is what we're going to be looking at for the next 2 academic weeks. Okay, and so let's look at the numbers here and what really makes this happen. Okay, so here we are. This is a penny doubled each day. So day 0, you start out with a penny. Day 1, you have 2, 4, 8, 16. And as you go through this, everybody who has chosen the $30,000 a day is still happy all the way up. They start getting a little nervous here. They're like, oh my gosh, day 24, 167,000, day 25, 335,000, and then at day 27 is where you who chose the penny, who waited patiently for the return, have come out on top. And this is what we are going to be looking at and what actually happened here and what are all the different pieces that fit together to make this happen. Okay, so what I want to do is I want to take a look at this exponential function. So here is our exponential function. All right, it is a function, meaning remember that for every input there is one and only one output. Okay, we have a, b, x minus h plus k. A, b, h, and k. We're already familiar with those. We learned those way back at the beginning here. And as I told you, they're going to keep coming back. And so again, if we have learned what a, h, and k do, then we're going to be pretty good with this stuff already. And we know what's going to be happening. So we have the initial amount. A is the initial amount. How much am I starting with? Okay, how much of this am I starting with? So like in the penny example, you were starting with a penny. If we were looking at a population of animals and we were wondering when they were going to be extinct, it would be what we would survey the animal species population to be at. If it was a bank account, here's $100 that I'm putting into the bank, then this is my initial amount. Where am I starting? We'll come back to B in a minute. H is going to shift the graph left or right, okay? And remember, it's always x minus. So if this was x plus 2, then that would mean it would be an x minus a negative 2, and that graph would shift to the left, okay? And then k is going to be this vertical shift of the graph moving off the x-axis up or down depending on whether it's negative. This is something new. It's also what we're going to call the horizontal asymptote. An asymptote seems like a dirty word, and yep, you probably snickered a little bit about that. But what this actually is this is an imaginary line that the graph comes infinitely close to. Okay? And we're not really going to focus on that so much. I'm going to ask you what the asymptote is, but we'll kind of work on that and maybe in the week 2 of this. And then last but not least is this b. This b is the piece that is going to actually be raised to the exponent. So whatever that exponent is going to be. And it's going to be a growth or a death factor or a decay factor. Okay? And we're gonna look at that and go into that a little bit in more detail. So, the life and death of exponential functions. Assuming that there is a fixed percent increase or decrease, meaning it is growing 2% a day, or your car is depreciating 0.5% every week, something like that, that it's fixed, that you have your savings account is getting a specific interest rate and it's not changing. Okay, that's what we mean. Then this is what it looks like. This right here, this 1 plus r, is the b that we were talking about. We're not really going to be focusing on h or k in this. We're just going to be looking at these growth and death kind of things. And this, unfortunately, is kind of apropos given the current circumstances of the COVID-19 virus and how quickly it grew and how, we're looking to get over that hump. All the numbers all the way up to that hump were fitting into this model here of this growth, okay? There was an initial patient, and then how fast it was growing, and then the exponential time and stuff like that, all right? So we're going to look at that. So this 1 plus r is what we call the growth factor, where b is greater than 1, okay? T is the time, and a is the initial amount, okay? And as I was saying, compounding interest, spread of disease, rumors, okay? How quickly things spread, all right? And we're going to look at both of these in a minute, all right? Look at some problems, okay? And then if there's growth, then there's going to be decay or death. And this is 1 minus r, okay? So let me go back to that other page for 1 second and give you like a quick example. So what we're talking about here is that there might be some number 3, there might be some function, f of x is equal to 3 times 4 raised to the t power, okay? And because this right here, which is our b, is greater than 1, then that means this function is growing. Okay? We don't know how fast it's growing. Okay? I mean, we do. It's growing actually at 300% because it's 1 plus r. Okay? And is equal to 4. So we subtract 1. R is going to be equal to 3. And that's a percent. Okay? And remember that, you kind of need to remember that as a percent, that's 300%. So that's a 300% growth. That's really fast. And this is going to be our initial. So for instance, like carbon dating. If we were archaeologists or paleontologists or something and we were on an archaeological dig and we found a dinosaur bone and we do the carbon dating and stuff like that, we're looking for how much carbon has actually left the bone itself. And that is the half-lives and stuff like that, and it's the decay factor. If we're also talking about like half-lives of radioactive material and how long it takes for them to be half of what they were. Okay, so this is so 1 minus r, this is our b. B is less than 1, and t again is the time, a is the initial amount, and r is the rate of decay. So for instance, we might, say we start out with 300. This is our initial amount, and we're at 0.9 to the t. All right, so this is our b. And since b is less than 1, then that means this is decaying or dying, whichever word. I don't really care which word you choose to use. All right, and remember that in order to get that 0.9, it's 1 minus r. So 1 minus r is equal to 0.9. I'm going to subtract 1, subtract 1. Minus r is equal to 0.10, or negative here. The negatives cancel. So r is going to be 0.10 or 10%. So this is 10%. Okay, that means it's decaying every time period 10% of what it initially was. So say if it was per day, if t was per day, and we started at 300, that means on day 2, right? Day 2, we would have 90% of 300, which is equal to 270. Okay? And then on day 3, we would have 90% of 270. So that is 243. Okay? Now, remember, here's where we started. So notice the difference here. 300, the difference is 30. This difference is, well, actually that's 27, so maybe I did something wrong. But no, I didn't do anything wrong. The difference between your numbers are going to slowly asymptote. The y equals k line. Okay? Examples: depreciation of a car's value, or any value of anything. Okay? Death from a plague or virus, as it may be. Stuff like that. So let's look at this. All right? I'm going to pause 1 second because I have to get up another program here. All right, so let's pause. It's not pausing. All right, so bear with me for a second. I apologize for that. I just need to get the calculator up on my screen. I don't know why some things are not working. All right, anyways, if it shows up, we'll get there. If not, no problem. All right, so let's clear this out. So let's look at this equation here. The population of Winnemucca, Nevada, wherever that is, somewhere in the middle of the country, okay, can be modeled by the equation P is equal to 6,191 times 1.04 to the t power, where t is the number of years since 1990. What was the population in 1900? By what percent did the population increase each year? So here we go. So what was the population in 1900? In other words, when t equals 0. So if I plug 0 in here for t, that means anything, remember your powers of your exponent property, anything to the power of 0, 1.04 to the 0 power is 1. Anything to the 0 power is 1, 6,000. So the initial population, right? Initial population is 6,191. And we look, here is B. The question is this number 1.04 greater than, equal to, or less than 1? And it is greater than 1, so it is growing. The population is growing. All right, and the question did clue you in. It said increase. So no problem there. And so I need to figure out what it's growing by. So I subtract 0.04 is equal to r. That's going to be our difference, and that is a 4% increase. Okay? So every year, right, because t is the number of years, since 1990, the population is going to grow by 4%. Okay? Question doesn't ask us what that actually is. Okay? It doesn't give us a time, but, hey, 5 years from now, we would just plug in 5 here, 1.04 to the 5th power, and multiply that by 6,191, because, again, we are always following orders of operations. Okay, so let's look at a decay or a death model. So radioactive decay. The amount Y in grams of a sample of iodine-131, which is a radioactive material, after T days, so see the T is different, up here it was years, now it's days, is given by the function Y is equal to 50 times 0.92 T. And right away I notice that this is less than 1, so it tells me that it's dying. How much substance did we start with? What percent of the decay? What percent of the substance decays each day? Sorry, typo. All right. So how much did we start with? What's the initial amount? Well, again, my model is A, right? B to the T. A is my initial amount, so that lines up with 50. So 50 grams of iodine 131 is my initial amount. And then I need to go after my rate. How quickly is this decaying? So B, remember, in the death is a 1 minus R, and that is going to be equal to 0.92. So I'm going to subtract 1, negative R is equal to 0, or negative, right? Negatives cancel. So R is going to be equal to 0.08, which is 8%. So this is 8% decay per day. And that's what we're looking at. That is the structure of the exponential function. Whether it's growing, the piece that is going to be raised to the exponent is going to be greater than 1. So in order to find out what the percentage is, I'm subtracting it. Okay? And from here, we have a death or decay. The number is less than 1. Okay? And so I need to subtract that from 1 to find out what that difference is. What is my decay per time period? All right? So let's actually do some math here. All right? And get things squared away. So bring that over here. All right. And you can do this on Desmos as well. All right. And I might switch over there in a second as well. But I got the calculator up and we'll look at that as well. At last count, in 2015, the species number of a particular spider was 121,000. The rate of decay is 2.5% per year. Let T be the number of years since 2015. Write an equation modeling the extinction of the species. When will this species be extinct? Okay? So that means, so remember our function. Our function is f of x is equal to a b to the t. So this is decaying, so that means it's going to be a, parentheses 1 minus r to the t. So I need to know what a is, and I need to know what r is. Well, a, we're told, is 121,000. Okay? And 1 minus 2.5%. So remember, 2 decimal places to the left, so 0.025 to the t. Now I can simplify that. 1, 2, 1, and this is going to be 0.975, right? Yeah, to the t. And that's going to be the equation that models, Okay? So at any point along the line, I can figure out when this is going to, when the species here possibly is going to be extinct. So let's get over here and let's, oh, nope, sorry. Let's go to Desmos. All right, and let me turn this on so you can see what we're doing here. I'm going to go into Desmos and wait for this to load up. Remember, you want to make sure that you are signed in so that you can always save your graphs and stuff like that. Be able to come back to them and sign in with Google. Okay, use your school account, and it's all set. So here I go. I want to type in that equation. So I can type f of x is equal to 121. Remember, no commas. Okay, parentheses 0.975 parentheses, and then shift 6 to the x. All right. Now it tells me that I graphed because I can see that it's graphing. The question is where is this? So remember, my initial amount is 121,000. So I could scroll the mouse button out, keep scrolling, and that's going to take a while. So I can come over here to the wrench, and come over here to the wrench, look at the y-axis and be like, hey, let me get way up here, 100 and let's say 25,000. There is something, all right, and years here, so let's maybe do x out to 100, okay? And I'm going to move my face over here so you can see the graph a little better. And this is what we're looking at, all right? We have this graph here, and it's coming down and down and down and down and down, all right? And we still have some to do here because I want to know, when is this species extinct? When is this actually going to hit 0 or 1, right? Anything less than 1 with half a spider isn't going to count. All right, so I want to give myself a little space on the bottom, on that y-axis, and I'm going to go out maybe another 100 years here and get down here. And I'm going to come back over here and I'm going to add this other equation, and it's going to be y is equal to 1. And I'm going to put that on the graph, and I'm going to move that up. And here it is, right? You can see, and I want to move down here till eventually these two hit. And I don't know where that is. I'm going to have to scroll in here, zoom in really close, and you can see that it still hasn't hit. And let's see, we can play with our numbers here a little bit, and we can say, all right, well, let's get this down to like 50. And we can kind of see, wow, it's still coming out many years here. All right. Now, granted, there are easier ways to find this, and we'll talk about that in a couple of weeks or so. But we're getting pretty close here. Are we there yet? Let's see. Nope. See, we still have a population of 9 here. So we're still close. When we're, coming out, I think it's, if I remember right, it's like about 400 years or so. We still have 4 spiders left. So you can see it's going to take a while, okay? That's the main point. Don't want to belabor that too long. You've already been sitting here for 25 minutes, and let's get back to this. So one other thing that I want to look at with regards to these that is going to play an important piece, that is going to play an important role here as we go forward is compounding interest. Okay, so it's a similar equation. Okay, we have in our initial amount, we have some growth here because we're talking about interest and it growing and the time. So P is our initial amount, R is the interest rate, N is the number of times that a interest is compounded. And compounded means, you know, like they can recalculate. When do they recalculate your interest? Is it every day, every month, every week, year, and stuff? And then how long have you actually invested? Okay, how long are you actually going to keep your money in? All right, so let's look at an account here, or a problem. You open a savings account at a local bank with $500. That's your initial amount. That's your P. The interest you is 2%, so that's 0.02, right? And is compounded daily. So time is going to be 365. How much do we have in the account after 5 years? So I just fill in the values that I have. So P is 500. Excuse me, 1 plus R, which is our interest rate, 0.02, divided by N, 365, over 365, N, and the time is 5. Now, that looks like a very crazy kind of equation. All right, and we're going to just plug that into our calculator. So I'm going to send you back over to our thing here, to our other screen. We'll make this a little bit bigger so maybe you can see it some better here. All right, so I have 500, and I'm going to put it in parentheses. And that is, let's see, 1 plus, and I'm going to open up another parentheses here, and I'm going to have 0.02 divided by our number of times it's compounded, 365, close that, raise that to 365, number of times compounded, N, times T, the number of years. And I'm going to hit enter. And you can see that after 5 years, at an interest rate of 2%, I'm going to have $552.58 in my account. And this is demonstrating the, you know, your typical savings account or whatever. So after 5 years, so A at 5 years is going to be $552.58. Okay? Hopefully this gives you a good grasp for the problems that we're going to be looking at this week. And remember that tomorrow, so your task today is going to be to view this video, take notes on it, send me a picture of those notes. Tomorrow you're going to watch the same video again, and this will be an ed puzzle. There'll be some questions there for you to answer and go through. And then on Thursday you will have a worksheet with a few problems to work through and stuff like that. When you're done with that, take a picture and send me those. And don't forget our optional virtual drop-in on Wednesday. Check the syllabus for the timing of that. I'm going to move it a little bit later in the day, so hopefully a few more of you will be up. Thanks, Patrick Roth, for that piece of advice. And yeah, and don't forget to check in on the daily check-ins and stuff like that to make sure you're all doing okay. Hope you are all well. Thanks for putting up with the 28 minutes of me talking. I really appreciate it, and let me know if you have any questions whatsoever. Take care.